So we're talking about Euler Paths and circuits. All right. Let's talk about. First thing we need to talk about is less objective. I can use graphs and the definition of circuits and paths to study a situation like the Königsberg bridge problem to determine if certain conditions can be satisfied. Now, if you're not familiar with the Königsberg bridge problem, go back and look at the bell ringer that I've added in there, and it gives you a lot of details. But we'll go through it right now. So the bell ringer is supposed to help you when you first get into class, and I forgot to put it in there. Unfortunately, you're usually my guinea pig. What's up, Jonathan?
Since we're doing it like this, people that can't get in, can they just do it on the board or something, or what? 'Cause I don't have a computer.
I'll give you credit. Okay, it's just a mastery check. The assignment is in there too. That assignment is a form. It's a Google form. Okay?
Where's the...
Okay, all right, about the opposite, like,
So the Königsberg bridge problem. The following figure shows the rivers and bridges of Königsberg, which is in Austria. Residents of the cities, for some reason back in the 15th century, 14th or 16th century, they occupied themselves trying to find a walking path through the city that began and ended at the same place and crossed every bridge exactly once. So in the video it talks about starting at the north side. Okay, so is there a path where we can cross every bridge exactly once and start and end at the same spot? Well, let's try it. Plug and chug is one way to determine if it works. So we're going to start here, go down this bridge, come to this island, go down the south bank, come over here, go up to this island, up to the north bridge, come up here, go there, and down. But we missed the bridge in the middle.
yeah, no, that's a lot of traveling.
So let's try it again. Let's start, and let's go across that bridge, come back, go here, go here, go here, go here, go here, go here, up.
You gotta go back.
You missed.
I've touched all the bridges except that one.
Yeah.
And what you're going to find is no matter how many times you try it, there is no path where you can cross exactly every bridge exactly once. Okay? And there's a algorithm to figure this out. And we talked about that word the first day of class. And I want you to understand that everything you do in math is a step-by-step process. Otherwise, it's known as an algorithm. Okay? Let me get over there so I can... All right, the bridge problem as a graph. Now, we just saw the map of the bridge. It's kind of like, that's the exact same problem right there. That's the map. This is what we call a graph. There's a gentleman by the name of Leonard Euler. That's how you pronounce it. E-U-L-E-R. It's Euler. I like the Houston Oilers. He's a famous mathematician. He turned his attention to the bridge problem, and his first step was to model the bridges. That's what this graph is. It's a model. The points are represented. The points or vertices are represent the land, and the edges represent the bridges. Now, if we look back at that picture, and I'm not going to go back, but if you look at the bell ringer, you can see it. There were two bridges from the north shore going to that one island, and there were two bridges from the south shore going to the same island. And there was one bridge from the north shore and the south shore going to the other island, and one bridge going in between there. Okay, the bridge problem is now stated. Given a graph, find a path through the vertices, or the points, that uses every edge exactly once. Such a path is called an Euler path. If an Euler path begins and ends at the same vertex, it's called an Euler circuit. Now I want you to think about that for a second. This is important. If an Euler circuit exists, so does an Euler path by definition. Now think about it. It says, if you find a path through the vertices that uses every edge exactly once, that path is called an Euler path. Now if you find a path that begins and ends at the same vertex, it's called an Euler circuit. Well, look at how it was defined. If an Euler path exists that starts and ends at the same vertex, then it is also an Euler circuit. So it's both an Euler path and an Euler circuit. So if you're looking at a graph and you realize that an Euler circuit exists, and the options are choose which one is most accurate, and it says Euler circuit or Euler path and Euler circuit, which one's most accurate? The one that says both, right? Okay. All right, basic concept of graph theory. A graph consists of vertices and edges. Singular is vertex. Plural is vertices, not vertexes. A vertex is a thickened point or a node. You'll hear the word node used in sometimes test questions or quizzes. An edge connects or bridges between two vertices. It could connect a vertex to itself. Yes, you'll see one loop back to itself. Edges are drawn as line segments, arcs, etc. Multiple edges between the same two vertices is sometimes allowed. All right. Let's look at the top example. Does a pathway exist? I want you to look at it carefully. Does a pathway exist where every edge is touched exactly once. So start. Somebody tell me what that pathway is. And if a circuit exists, tell me what that pathway is.
I can't see it.
It touches the edges only once.
Uh-huh.
I mean,
Paths,
they
right?
don't, but yeah.
They're all paths.
They're all paths? You sure about that?
I
No,
don't
that
know.
last one is, well,
You
never
go
mind, never mind.
A, B, E, D, C.
Yeah.
A, B, E, D, C?
Yeah.
Okay, now you misunderstand the definition. You've touched every vertex exactly once. It says to touch every edge exactly once. So, if you go A, B, E, D, C, you can go back up to A, go to B, and go to D, then every edge is touched. So now we've just created an Euler path. Where did it start?
At A,
Where did it end?
at
A,
E.
B.
Is that an Euler circuit?
No.
By definition, it has to start and end at the same vertex, right? So we know an Euler path exists. Okay? You can start anywhere, almost, and it'll do it. There's a trick to it. And we'll get into that before the end of this lecture. How about this one? The whole point here is to cognitively give you some way to think about it.
I don't see a path.
You don't see a path?
I mean,
We can
not a
go
path,
That's not what it is.
Tell them.
at
A,
any
B,
point.
E, D, A, C, F, G.
Meaning like, I don't see where you could start and where you could end at the same point.
Okay, I'll give you that. Go one further. Does a path exist?
Yes.
Show me.
It's easy.
Hang on.
Okay, so let's say we start at C. Oh, you can start at A, C, F, D, A, B, E, G, F. We still missed the D and E segment.
Yeah.
A path exists if all edges are touched exactly or crossed exactly once.
That's not the edge right there?
Yeah, but that edge didn't get touched by that pathway.
But you have.
Okay, let's start again. Let's start at E. Okay?
D.
E, G, F, C, A, B, E, D, A. We still missed D to F.
How?
We didn't touch it.
Why did you touch it?
Because you can't cross the same path more than once to get to it.
But you didn't cross that path.
But you have to go all the way around.
You have to go all the way around to get to it. Now watch. Watch, DeAndre. Start at F. F to C. C to A to B. B to E. E to G. G to F. F to D. D to E. But we didn't cross A to D because we can only touch those pathways once.
But you didn't say have an end, have to start with the same letter, end with the same letter?
I was saying that the circuit does not exist.
Yeah.
We already proved that. Now we're saying that the path does not exist because we can't touch every edge exactly once without crossing a path.
Yeah.
In other words, you're going to take away that whole thing. How about this last one? There's an easy way to determine that the pathway or the circuit does not exist.
Look at power.
Can somebody tell me why and
Look
what
at
you're
six.
talking about?
It does not,
The six.
connect to the three.
It does not connect to the 3. The 6 does not connect to the 3.
Yeah, that's
Well, it doesn't matter. I mean, let's say you start at 6. You see that one thing that goes back to 6?
It's a loop.
It's called a loop. You're right. Exactly. That's great. DeAndre, that's awesome. That's called a loop.
I didn't say that.
Who said it? I'm sorry. I apologize. I thought it was DeAndre.
I thought it was him too.
With these masks, I can't tell whose mouth's moving and stuff. But see, if we go around to 6, we touch that path exactly once.
Yes.
Oh, okay. then
And there's only one pathway leaving 6, right?
Okay.
If we're going to go back to 6, because that's where we started, we'd have to have another pathway back to 6, and we don't. See that? Same thing, we start anywhere else, we have to go to 6 to hit that loop, and when we hit that loop, we're done at 6. So we know a circuit doesn't exist. What about a path? Let's go here, 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 here. Oh, we missed this one.
No.
No, you're right. No pathway exists. So this has no path and no circuit, no path, no circuit, a path and no circuit. Okay? All right, here's Euler's contribution. He paved the way in solving many computer science problems of today by creating a new mathematical discipline centuries before the first computer was created. Graph theory is used a lot. Can anybody tell me an application that you use every single day on your phone that uses graph theory? Okay, the internet is a way. Yeah, you're correct, because they find the fastest way to get a connection. What's another one you use every single day that uses the internet? Say that again? Snapchat? Well, possibly, because it's using the internet, but I'm talking about some useful tool you use that might use graph theory.
Calculator.
Damn, edit.
How do you get to someplace you ain't never been?
GPS.
Yeah, GPS.
How do you think they know the quickest route?
For what?
By looking up.
They use graph theory because they know all the possible pathways to get from one place to another, and they find the shortest pathway. We'll talk about that more in weighted graphs in the third lesson later this week. Okay? So, let's keep going. Alright, a graph in which every edge is crossed once, which starts and ends at the same vertex, is called an Euler circuit. We just said that. That's a definition you must know. Okay? A graph in which every edge is crossed only once but starts and ends at a different vertex, or different vertices, is called an Euler path. Circuit starts and ends at the same vertex, but it touches every edge exactly once. A graph touches every edge exactly once, but it starts and ends at different vertices. Now there are rules to determining quickly if a circuit or a path exists. But we have to talk about one more term in graph theory. Alright. Determine the following graphs of Euler circuit or Euler path exist. We already did that. What makes a graph an Euler path? What makes an Euler circuit? And what makes a graph neither? If an Euler circuit exists in a graph when all vertices have an even degree. What is a degree? We'll talk about that in a second. An Euler path exists in a graph when two vertices are of an odd degree and the remaining vertices are of an even degree. Neither Euler path or circuit exists when more than two vertices are of an odd degree. Now, what makes a vertex odd or even? Let's talk about that. Let's look at it closely. A vertex's degree is defined by the number, it's not in here, I don't know why, it's defined by the number of edges that actually enter and exit the vertex. So here, I want you to look at that for a second. Let's go back and look carefully. Alright, let's look at this real quick.
I got two right.
By this definition, the degree of a vertex, first of all, somebody tell me what is a vertex? On this graph, what's a vertex?
Vertex are the letters, the A, C,
The dots,
D,
right? The dots. Because down here they're numbers, right?
Yeah,
So whatever the label is for that dot. Well, what if the edge was labeled?
that would be the vertex.
That would be the.
Well, no, that wouldn't be the vertex. It would still be the edge, it's just labeled.
Alright.
Typically, we're going to label it like we do mathematically. We'll say this is edge CA, or AC, whatever you want to call it. But the degree of a vertex is the number of edges that intersect there. So look at the first graph on the top. What degree is vertex A?
3.
3.
Exactly. What degree is vertex D?
3.
What is the
That's
degree of vertex E?
That's 4.
Let's see.
E?
E is
D is 2.
Time out.
It's one.
D is 4. He's right.
Yeah, D's
D is not 3. Do you understand that?
How about that? I didn't think I'd pick.
The
Where?
bottom little thing right there, right?
Look right here. A. How many edges intersected
Oh,
A?
no.
How many lines intersected A?
4.
At A? 1, 2, 3.
Three. What?
Time out.
C goes to A, that's 1. D to A, that's 2. And B to A, that's 3. 3
Oh, you
edges.
talking about like that? I'm thinking the opposite.
Okay.
You talking about edges. I'm
D.
all of them.
D has edges. E to D, B to D, A to D, and C to D that all intersect at D. That's a degree 4. How about D on the second one? What's the degree of it?
1, 2, 3. 3.
Okay. How about B?
B.
2.
All right. Now I want you to remember what I just said about that definition of degrees. We said we know that a pathway exists if two of the vertices are odd and the remainder are even. So look at the top one. We already discovered by plug and chug that it was a path but not a circuit. A circuit means that they're all even. Now this is simple to understand.
I mean, all of those are even.
No, they're not. A's
Top one?
odd.
Huh?
A's odd. So is B.
3.
How?
Because
That's
1,
three.
2, 3. 1,
I'm
2,
thinking
3.
about the length of the line.
No, not the length of the, just I want you to do the number of lines that intersect it, okay?
You're right, yeah. I feel
Okay? So A and B are odd. What about E? Is it even or odd?
It's odd.
Degree 2, right?
Oh,
E is degree 2,
oh,
right?
yeah.
What about D? Degree 4, that's even.
That's even.
C is degree 2, even. So we have 2 that are odd and the rest are even. How about this? A is odd, B is even, E is odd, G is even, F is odd, D is odd, and C is even. We have more than 2 odd vertices, which means neither a path nor a circuit exist.
So if there's more than 2 odd,
That's
Then
exactly,
neither
that's what I
path
said in the next,
or
I'll show you that again. This bottom one, you can omit it immediately. Why?
The 6.
because all of them.
Well, the 6 has 1, 2, 3 odd. That's odd, right?
Odd.
What? In a loop, you have to count 2 edges. Think about that. There's only 1 edge, but 2 edges intersect, the same edge, 6 to 6. It intersects is going out, intersects it coming in. So that's 2, 3. That's 6 is degree 3. Okay?
It's only 2 with. Well, it's 3 of
4
them,
is degree 3,
4
3 is 2, 2 is 3, 5 is 3, and 1 is 2. There's 4 odd and 2 even.
Yeah.
Okay? Now, a circuit exists when all of the vertices are even. Okay? A circuit exists when all of the vertices are even. Okay? There's a part of that last slide that's missing. I don't know where it went, but it describes the degree of each vertex. Okay, an Euler circuit exists in a graph when all vertices are of an even degree. Can somebody tell me conceptually why that's true? Why would that be true? DeAndre, come on, man, don't close your eyes. I can't sleep in class, so you can't either. It's not fair. I'm tired, just like you. I'm more tired than you. I got 5 kids, and I coach tennis.
I got 3.
You got 3 kids?
Yeah.
The goats in your barn don't count.
I don't even know.
I got another. I got 3. I got 5 children and 1 kid. There you go. I got 1 goat.
You want to meet him?
No, I don't.
I got a newborn right now. In my phone.
In my phone. All right. So think about this for a second. Think about this for a second, folks. Why would all the vertices have to be even for a circuit to exist? If you want to start and stop at the same point and hit every edge exactly once.
I'm gonna lie to you. Out of all my years of being in math, I ain't never heard about this.
Because it's a brand new concept. That's why I do it first, so you got time to think about it. Okay, so think about this. If you're going to start and stop at every vertex, or if you're going to start and stop at one vertex, you have to go in and out of every other vertex. So what does that mean? You have to have multiples of 2 for every vertex, right? So if you leave A, and you got to come back to A, eventually it's going to be even, because you have to leave it. Even if you go back and leave again, you have to come back, right?
Yeah.
So it has to be even. The entrance and the exit have to be even, an even degree. So do the rest of them, because you have to enter it and leave it to get back to A. Now that makes sense, doesn't it? Logically, all of them have to be even for it to be a circuit, okay? I'm going to have to update this slideshow, because I just realized that's not in there.
You really gotta.
Anyway, I'm going to launch you with this. Leonard Euler introduced much of the mathematical notation we use today, such as the notation f of x, function of x, to describe a function in the modern notation of trigonometric functions, cosine, sine, tangent. He was the first to use the letter e for the base of the natural logarithm, now known as Euler's number. That's why it's the letter e, because it's named after him. How many of you remember doing logarithms last year? Remember natural logarithms? Log of e? That e was named after him.
In what, algebra 2?
Yep.